Okay, so now we'll talk about RowHammer. And this is really an example of this part over here. How to design fundamentally secure, reliable, and safe architectures. And basically, this is the high level. You can predictably induce bit flips in commodity DRAM chips. And when we first did the study, we showed that more than 80% of the tested DRAM chips are vulnerable to this RowHammer problem. And this is the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. And if you know of an earlier example, please let me know. Then I will change my slide. But this is the first example that we have found. And as a result, people are writing really interesting stuff like this, claiming that software is not important. It's really all about physics in the end. And when I talk about security, I actually use these slides, and this is going to be more fun. This is a very famous psychologist, American psychologist, Abraham Maslow. This person, actually, it's good to study his life also, but he dedicated his life to understanding why human beings do the things they do. And he developed a theory of personality and motivation, basically. You can see the books that he's written. He's probably more famous for this thing, which is Maslow's hierarchy of needs. How many people have seen this in some context? Okay, good. This is actually not, clearly actually it doesn't exist as much in engineering, but he's had a lot of influence in politics, economics, psychology, sociology, all of those fields, and everybody uses this in the end. So I'm going to use this within the context of computers. Basically what this says is you have to have your basic needs satisfied before you can think about higher level needs. Before you can think about even higher level needs, you have to go through this hierarchy. If you want to deal with highest levels of abstract art, for example, you should make sure that you're not dying before that, right? This is one example. Basically, you need to start with reliability and security first. If you're starving, who cares about highest levels of art? I think being in Italy, it's good to think about this because Italy is very good at highest levels of art. But it got there because it was able to get rid of or at least satisfy all of these beforehand. I also use this example, this bridge, as an example of reliability and security. I use this in my freshman class. This is a bridge over a beautiful part of the world. It's over Hood Canal, very close to Seattle. Now this bridge is nice, but it doesn't exist anymore because this is what happened to it 6 months after it was built in 1940. Why? Because a bit flip happened in this bridge. You can liken this to a bit flip in current infrastructure. So I use this bridge because it's infrastructure, right? If you think about computing, it's infrastructure also. We're building the infrastructure that's used by everyone, and people are going to depend on it even more than this bridge, actually. And if we have these bit flips that break the infrastructure, then fundamentally everything is broken. Reliability, security, and safety. And this bridge actually is an example of it's a reliability problem. It actually did this for some time. It's called aerostatic flutter, and there are a lot of studies related to this. You can watch the video actually of this bridge doing that. It's called Galloping Gertie. Actually, no one died in this case. Actually, a single dog died, unfortunately, because it got stuck in a car over there. A professor was trying to understand why the bridge was doing that, and interesting. Professor lives. Anyway, basically it's an example of reliability and safety. So it's another example. These folks are building Manhattan after World War. They're sitting on this infrastructure that they assume is reliable. They're very happy. If there's a bit flip in this infrastructure, they will not be happy in a second, right? So we're building all these computing devices and we're relying increasingly on them. That's why we need to build this infrastructure really well. If it's prone to these bit flips, we're going to have a lot of problems. And I think one of the problems is security in the end. Security, in my opinion, is really about, in the broad sense, it's really about preventing unforeseen consequences. We designed this infrastructure. It's going to be used for something. It's going to be used for something else 5 years later. There will be security problems. How do we prevent those security problems? It's really unforeseen at that point because you cannot imagine what people will use these infrastructures for, right? It's even worse than bridges because bridges, you know what people will use them for the most part at least. Okay, that's why I think computing is at a very critical point today, more than yesterday, let's say. So I think the connection to the DRAM scaling problem is obvious at this point. If you get bit flips in your DRAM, it's vulnerable to security attacks. It's not vulnerable to safety problems, and we've already talked about this. As you reduce the size of the cell, it becomes more vulnerable to bit flips. And there's really a lot of evidence from the field. The study I've already shown, as the cells become closer to each other, they become more vulnerable to these bit flips, to different sorts of noise. As a result, you get pictures that look like this. The error rate increases as the memory capacity increases. Okay, and you can read the paper for a lot more detailed analysis. We actually open source a lot of stuff also. There's a nice web page that my student Justin prepared where you can put in the parameters of your system, and it tells you the error rates that you expect with the numbers based on the models that we developed in this paper. And as I said, we were developing these small-scale infrastructures to test DRAM scaling issues. This is our first infrastructure. It's FPGA based. It was done collaboratively with Intel. It took a lot of time to bring this up. As you can see, it's makeshift. And then this is our second infrastructure. We wanted to study the retention time issues, as I will briefly discuss, because we believe that retention time is a big problem in DRAM. If you want to scale DRAM, we want to understand refresh problems, and we want to get rid of refresh as much as possible. And I'm going to give you basic ideas related to that. And this is another infrastructure. This is actually where we did the RowHammer studies, and this is the open source infrastructure as I mentioned. So you can actually do these studies yourself. They're open source. A lot of people have replicated them. Other people are using this infrastructure to find out other stuff in DRAM. It's very nice. So the reason we built this infrastructure was this: to understand the data retention issues. How long can a cell retain data? What are the factors affecting those data retention? And can we get rid of refresh as much as possible? And at the time we were doing these studies, DRAM chips were being refreshed every 64 milliseconds. We knew that they were going to be refreshed more often in the future because this is a big scaling problem. Actually, if you go and look at the LPDDR chip today, it's refreshed every 32 milliseconds. So refresh rates are increasing. But we asked the question: do we have to refresh every single cell every 64 milliseconds? And the answer is no, because the retention time profile of a real DRAM chip looks like this. Basically, there's a very small fraction of cells that you need to refresh every 64 milliseconds because they happen to be weak. An overwhelming majority of cells, you don't need to refresh as often. Why? Because they're strong. And this is because of process variation. Most of it is random process variation. And the process variation essentially leads you to a distribution that looks like this. Now, if you see this picture, you can immediately say, why don't I design a controller? Well, one of the ideas could be, why don't I design a controller that refreshes different cells at different rates, right? Figure out the retention times. That's exactly what we did. We showed that you can do this with very low overhead. I'm not going to go through details. And if you actually do that, you reduce the refreshes by 75%. If you do the math over here, right? Now, it's not as easy, it turns out. Clearly, the retention time is dependent on the location of the cell, but it's not only that. The retention time is dependent on the value of the cell and the cells around it, because the interference, the amount of coupling capacitance that you get is very much dependent on the charge stored in this cell and charge stored in the cells around it, which is dependent on the value that you store. That's unfortunate. And also, it becomes difficult because the retention time of a cell is dependent on time. It's dependent on random effects. So what happens is, because things are not reliable, there's an error mechanism in DRAM that's called variable retention time. Once in a while, randomly, charge gets trapped in the access transistor, and when charge gets trapped in the access transistor, charge leaks from the capacitor really fast. This is called trap-assisted gate-induced drain leakage in DRAM. It's also called variable retention time. Because of this process, you lose charge really fast and your retention time goes down a lot. Now, it turns out this process is completely random as far as we know. We actually did a lot of studies to understand this and to model this. Currently, we're not able to model it, except we just realize that it's a random process. And it's a quantum-like effect, if you ask me. It becomes much worse in smaller technologies. It's a random quantum-like effect, and it's increasing. So this is the reason why it's very difficult to determine how often you need to refresh DRAM as you reduce the technology size, because this problem becomes worse. And I believe actually some of the errors are slipping into the field because manufacturers are not able to perfectly determine the refresh rates. Anyway, this is fascinating. As you can see, I can talk about refresh a lot also. But because of these issues, it's not easy to exploit this picture. So how do you exploit this picture? Basically, you design intelligent memory controllers in the end. That's essentially what we did. This was our first paper in ISCA 2012. Basically, we said that this is a good phenomenon to exploit to get rid of refresh. And then we built our infrastructure to say, okay, it's not that easy. Here's the things that you need to solve to actually build that controller. And then we actually wrote a lot of papers talking about how to solve that problem. And it's not easy, I think. There's still room for improvement here. So this is one solution to the problem, for example. But there are other solutions that target different parts. So this is another solution. So basically, how do you profile the DRAM quickly to figure out what refresh rate you should use for which cells? And you cannot do this once. You need to do it while the system is operating because of what I just said, because the retention time changes over time. Right? That's the idea. And this requires an intelligent controller for sure. And these are examples of intelligent controllers. It's actually the latest work that we published in DSN in 2019, which talks about how do you actually do this in the presence of on-die error correction. Okay, well, the reason we built all of this was actually to understand retention time issues, but we also knew that other errors would be happening in scaled memory technology. Read disturbance was one of them. So while we were doing these studies, we were doing other studies also, and we found out that you can predictably induce errors in most DRAM memory chips. Now this is known as the DRAM RowHammer problem. As I said, this is a widespread, simple hardware failure mechanism that can create a widespread system security vulnerability. So let's take a look at what this is. So at the very basics of it, it's a read disturb problem. Whenever you read some cells, you disturb some other cells. And this is very fundamental to any memory technology. Flash memory has it, SRAM has it, hard disks have it, DRAM also has it. Now the interesting thing about DRAM is it's directly exposed to your programming language. Whenever you do a load or store, you're directly interacting with it. With flash memory, you're not doing that. You're going through a huge software stack. So if this sort of thing happens in DRAM, it's bad. So let's take a look at the read disturb problem in DRAM. So if you want to read a cell in DRAM, you activate the row of cells, apply high voltage to it, that's called an activate. And then if you want to read something else, you close this row, meaning you apply low voltage to it, that's called a precharge of the array. Now if you do this repeatedly, activate precharge, activate precharge, activate precharge, activate precharge, activate precharge, activate precharge, enough times before the cells get refreshed, it turns out in most DRAM memory chips, cells in physically adjacent rows, if they're vulnerable, they flip from 0 to 1 or 1 to 0, depending on the encoding that happens. But they basically lose their value. You cannot recover it. Yes?
Is this vulnerability associated with the manufacturing process?
Yes, as we will see. It's really a scaling problem in the end. So why is this happening? Because cells are too close to each other, and whenever you're doing an activate over here, you're really affecting adjacent rows. So there are multiple mechanisms that are discussed in the paper, but let me give you the one mechanism. Whenever you're activating this row, applying high voltage to it, what happens is because things are not enough isolated from each other, you're slightly activating this row also. Now that slight activation causes some vulnerable cells to leak charge. And if you do this activation many times, these cells leak charge many times. And if you can squeeze in enough activations to a refresh interval, some cells will lose their value before they get refreshed. That's the idea. Now, as with technology scaling, what has happened, the cells become closer to each other, and this effect becomes bigger. So you need to do fewer and fewer activations to induce these effects as the cells become closer and closer to each other. And that's exactly what we've shown in our paper. So basically we call this hammer draw, victim rows, and we've analyzed a bunch of chips from 3 major manufacturers who shall remain nameless, but you can guess who they are because there are only 3 major manufacturers in DRAM today. But I mean, it's not, I don't want to say it's not their fault, but it's all of their fault in the end. In the end, all of them have the same problem. It's not like one of them is bad, the others are good. So basically more than 80% of the chips are vulnerable. And it's a scaling problem because these sort of errors did not exist in chips that were manufactured before 2010. You can see that the error rates are 0. The first appears in 2010. And all of the chips that were manufactured between 2012 and 2013 that we tested are vulnerable. And again, it's not manufacturer dependence. Manufacturers have error rates all over the place, and they all overlap with each other, as you can see. Okay, basically this is a scaling problem. So why is this happening? I think I've already said this. I'm going to skip this. This is because of the cell-to-cell coupling and interference, and we already said this also. So clearly this has a lot of higher level implications actually. You have a bit flip in the device. If this gets exposed to the program that's running, now first of all it could be a reliability issue, but it could also be a security issue, as we will discuss. So how does it get exposed to a program that's running? This is a program that we wrote when we released the paper. You can download it from here actually. It's only 6 lines. It's a user level program. It requires no privileges in the system. Anybody can run it basically. And what it does is it selects address X and Y such that they map to the same bank like this, and it basically bypasses the caches, bypasses the row buffer such that it does this. It ping pongs activates to X and Y. And if the chip is vulnerable, hopefully it will lead to errors. Now, of course, it's not the best program. It turns out you can optimize this program. So, for example, Google folks used our insights from the paper, and they selected X and Y such that there's only one row sandwiched in between them. And they hammered from both sides. It's called double-sided RowHammer. And they show that you can induce even more errors than we have shown in our paper 1 year later. So you can actually optimize this program, and different architectures have different sequences of instructions that can maximize the error rates. So with the program that we had at the time in 2013, basically we showed that Intel and AMD memory controllers are able to induce errors in the DRAM chips, and the errors are correlated with how fast you can access memory. But there's nothing special about Intel and AMD. All of the processors actually have memory controllers that are able to do enough activates to induce these errors if the chip is vulnerable. So it's a real reliability and security issue. And when we first wrote the paper, we said that memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other addresses. I still believe this. I think this is very fundamental. We should not change this at all. We should have memory isolation. And we said in the paper that we demonstrate a proof of concept attack, but somebody can actually take this and build an attack where you could actually gain kernel privileges and hijack the entire system. And while we were working on it, these good folks from Google Project Zero, I would actually recommend reading Google Project Zero blogs. They do a lot of blogs. Recently they published a study where they showed that there are a lot of exploits going on in an iPhone, for example. I think they showed 14 different exploits and how to do them. And of course they talked with Apple, so that Apple patched it before that. So they actually showed in this particular blog that they could exploit the RowHammer bug to gain kernel privileges. They call it a bug, I call it a failure mechanism. So this is beautiful security engineering. This is actually a copy and paste directly from their blog post in 2015. They basically said they learned about the problem from our work. They tested a selection of laptops and they replicated the problem. And they built two kinds of attacks. One of them takes over the Google native client. You get out of the sandbox so that you can actually, you're not in the virtual machine environment anymore, which is interesting, but not as interesting as the second one. The second one actually, you run as a user level program and you take over the kernel completely, so you hijack the system. And you can read the blog post for more detail. It's beautiful security engineering, but basically it induces these RowHammer bit flips, and it's able to induce, the key idea is to induce bit flips in page table entries, where the page table entry points to the page table of the program itself. Now, if you're able to induce a bit flip in your page table entry in such a way that you gain write access to your own page table, now you gain complete access to the system because you're able to write to your own page table. You can change all of your permissions to the highest level of permission. That's essentially what they did in one sentence. Of course, it's not as easy, because now you need to be able to do this. And if you really read this blog post and watch their Black Hat presentation, it's beautiful system security engineering. If you want to do hardware security, this is actually a really good example of it. But I'm not going to do that because it will take some time. Then we will only be talking about RowHammer. But basically, people started thinking RowHammer is really bad. In the end, I like this intuitive explanation from a very famous hacker on Twitter. He wrote that it's like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you were after. So if you're tired of my lecture, and if you're stuck in this room, and for some reason the doors are locked, start banging on the walls and magically the door will open and you can exit that way. Okay, I like this sort of intuitive explanation. That's why I like putting it. So I'm not going to go through all of the literature on RowHammer. I'm going to recommend that retrospective that we wrote, but there is a lot of really, really interesting hardware security and systems engineering here. Like Google Project Zero is very nice. I think there are a bunch of other papers. This is actually from a longer set of slides from RowHammer that I'm not going to talk about here, but I'm going to give you a couple of examples with pictures in a little bit. So this is actually continuing. There are two papers I think that are coming up next year in 2020. One of them is called RAM Bleed. Maybe I have a picture of that later on. Okay, one of the things that's really interesting is when we first wrote the paper, the first people who read the paper, I believe, were these memory testing folks. The folks who develop the memory test engines. You probably have run this on your computer, or they run sometimes when you boot up. So basically they said that they designed a test to detect RowHammer. I don't think their test is perfect. But the really fun part over here is after they designed the test, they started getting a lot of calls and emails saying, actually, we get a lot of failures in this test. Why is this happening? And they basically had to write on their website that the errors detected during test 13, RowHammer test, are, albeit exposed only in extreme memory access cases, RowHammering, are most certainly real errors. So don't worry, everybody's experiencing them. It's really interesting to read some of these. And I don't know if this website is still there, but last time I checked it was there. So we said that basically you couldn't develop these attacks, and other people developed these attacks. This actually worked from, actually a lot of people who worked on Meltdown and Spectre worked on RowHammer before. They got really interested in these hardware security problems, and then they started getting even more interested in the hardware security problems, and they found out Meltdown and Spectre. I believe there is something else that's coming afterwards. So these are some folks from TU Graz. A subset of these folks worked on Meltdown and Spectre later, but they first showed that you could gain unrestricted access to systems of website visitors by exploiting RowHammer through JavaScript. I won't go into a lot of detail. Clearly, you can read the papers. These are all published in top venues. This is another paper that was published in CCS from Vrije University in Amsterdam. They basically, this actually, I really like this a lot. They basically released this app, Android app, that could get to your Android phone, and it basically finds out which parts of your memory are vulnerable to RowHammer, and it exploits the deterministic memory allocation patterns that you have in the Android operating system to fool the operating system to allocate a page table entry for this process in a location that they knew is vulnerable to RowHammer because they profiled the memory. So they actually fool the operating system to allocate a page where they want, and then they hammer that page and they gain complete access to your phone. And that's why it's deterministic, because the memory allocation patterns that you have in the operating system are deterministic. Okay, and then later folks show that you could do these attacks much faster with a GPU. You could do these over a remote direct memory access engine. If you're in a data center, for example, you could hammer some other server by doing remote loads and stores. And these folks actually did exactly the same thing at the same time, but these folks were faster to publish the top conference. So these folks have an archive paper at the same time. And this is the work that's coming up in 2020. These folks show that even if you cannot hijack a system with RowHammer because some other protection may be in place, you can leak data by hammering some cells. And there are other stuff, and this is potentially one other attack to your system. If you're getting all these bit flips, this could be an attack or a solution, right? Hopefully it's not. It's neither. So let me go into a little bit more detail about RowHammer. Basically, there are some causes to it. I already talked about electromagnetic coupling, but we did a lot of studies to understand the problem. We're actually doing a lot more studies in newer technologies, and the problem is getting worse actually. Although people are developing solutions, that's the good part. So we tested 129 modules, and we showed that the distance between victim and the aggressor address, at least from the memory controller's point of view, are mostly adjacent. Basically, memory controller has addresses x and x plus 1. Whenever you hammer x, you get errors in x plus 1. Right? But that's not always the case. There are some cases where things are non-adjacent. You hammer x and you get errors in x plus 3, for example. Different rows. Now, we believe these are actually physically adjacent, but internally DRAM does some address remapping to improve reliability and improve reliability in general, improve power also. As a result, memory controller doesn't know which row addresses are adjacent. In some cases, not in all cases. Clearly, in most cases, they're adjacent. So this is actually going to affect the solutions, because one of the solutions will be that we're going to propose, whenever you access a row with very low probability, refresh the adjacent rows. Physically adjacent rows. But physically adjacent rows are not logically adjacent, as you can see over here. So if this mapping is not exposed to the memory controller will not be as effective in that solution. So there needs to be more information communicated between the memory controller and memory to be able to enable such a solution. That's why it's good to understand the picture that looks like this. Okay, so another solution could be reducing the access interval. Basically, how fast should you be able to access a row repeatedly? And today, well, in the test we've done, it was 55 nanoseconds. Less than that was not allowed. But if you want to get rid of all of the errors, you want to increase that interval to 500 nanoseconds, which is not a good idea because it reduces your performance clearly. But this is clearly one example way of getting rid of the errors. Maybe not the best way. Another way of getting rid of the errors is increasing the refresh rate of DRAM, basically refreshing more often. As you go from right to left, we're increasing the refresh rate. Here is the nominal refresh rate. And as you expect, as you go from right to left, errors should reduce. And these are the curves that you would get from 3 major manufacturers, the worst device. But if you want to get rid of every single error in the system, you need to increase the refresh rate by 7x. So this is not a good solution also, because remember, we want to get rid of refresh as much as possible. Okay. So this is also interesting. Data pattern actually affects the errors a lot, and other people later exploit that. If you have a data pattern that looks like this, capacitance coupling is low because all of the values are similar. Here the capacitance coupling is a lot. As a result, you get an order of magnitude more errors here. So if you want to hammer someone and hijack their computer, you'd better massage the error pattern, the data pattern that they have in their system first. So there are a lot of other results. Basically, RowHammer vulnerable cells are not the same as weak cells in terms of refresh. These are two different types of error mechanisms. There's almost no overlap between them actually. Now they're both based on charge leakage, but they're different forms of charge leakage. One is hammering based charge leakage, the other is electromagnetic coupling, the other is really natural charge leakage through the RC pad. Errors are not strongly affected by temperature. Retention errors are actually very much affected by temperature. At very high temperatures you leak a lot. Errors are repeated. This is actually the worst part. This is really causing the security problems. Basically, if you are able to flip a bit, you're going to be able to flip the bit again and again and again and again and again next time. So it's not random. You can predictably flip bits. And this is really the cause of the security problem in this case. Now, if you can do this with some other retention errors, for example, I believe retention errors are also security problems. No one has published anything related to that yet because it's a bit harder to do. But I believe those could be security problems going into the future. Okay, so people sometimes say, can you actually correct these errors with error correcting codes? We showed in our paper that not with simple error correcting codes at least, because you get at least 4 errors per cache line. This is actually interesting because I presented RowHammer in a supercomputing conference one time, and the next person came up to the stage. He's a good person, but he was from Micron. And he started his talk. His talk was on a different topic, but he started with his talk saying, I have a solution to RowHammer. It has 3 letters, ECC. Now, I didn't say anything, but recently in 2018, in IEEE Security and Privacy, I think some folks published a paper showing that even if you have ECC, they could hijack the system. So we knew that before, clearly. There were not attacks, but if you get this sort of errors, as many as 4 errors per cache line, somebody is going to exploit that. And I don't think ECC is a good solution. We're going to talk about solutions very quickly in a little bit, but ECC is a very broad solution. If you don't know your error mechanism, if errors are completely randomly distributed, error correcting codes are a very good way of protecting against them because you have no idea where the errors will appear. RowHammer is not like that. RowHammer is actually, you know exactly when you will get the errors. So why don't you design a mechanism to just very efficiently detect that sort of issues. Maybe not even detect, very efficiently adapt to the error pattern that you're getting. Okay, this is actually very interesting. Also, this is getting worse. Basically, there are more cells and rows that are being affected by the aggressor. And actually, we showed that cells are affected by 2 aggressors on either side, and this is exactly what Google Project Zero used to do the double-sided row hammering. Okay, if you're interested, this is the original paper that we wrote in ISCA 2014. And as I said, we wrote this retrospective paper recently that covers almost all of the work that built on RowHammer, maybe not the most recent work in 2020 or so. Let's talk about solutions a little bit. I think this is also very important. We basically need 2 types of solutions. One is immediate, because there are chips that are out there vulnerable in the field. How do we protect them? Now we have limited possibilities here, especially because we don't have intelligent controllers. We have very limited programmability in our memory controllers. But in the longer term, I think we need to think even broader because there will be RowHammer-like issues. There will be other issues also. How do we protect these future DRAM chips? So we can enable a wider range of protection mechanisms. And let me cover some of these solutions over here. So this is a slide from our ISCA presentation. We can make better DRAM chips. Usually it comes at a very high cost, like isolate things better materials, not so easy. Refresh frequently across the board. This is the immediate solution that we're going to see, but it's not good in general. Sophisticated ECC, we already talked about cost and power. Access, I think this is very interesting actually. If you can develop a very low overhead way of detecting when you're accessing something very rapidly, this could be a good solution. But the key is, how do you develop that low overhead way of detecting? When we first wrote the paper, we didn't have that. Later, people actually developed mechanisms. I think we're still not there. We don't have this extremely low overhead way of detecting which rows are being rapidly. I think this still requires more research over here. I don't believe these are good solutions in general, refreshing frequently and sophistication. I don't know enough about this one because, I know a lot about this one, but I don't know how to solve the problem basically. Basically, this usually requires new materials or a lot more distance between the cells, and they both are expensive in the end. So I think there's research to be done in this area. But let me, I'm going to skip these naive solutions because they don't work well. So this is the immediate solution that's employed in the field today, because we don't have enough programmability in our memory controllers. Apple was nice enough to release the security patch where they said they increased the refresh rates to solve the RowHammer problem. They didn't tell exactly how much, probably 2x. Actually, I bet it's 2x, but 2x is not enough from our experiments. Actually, our experiments were based on results where we could hammer DRAM as fast as we can. Later, people showed that you could hammer it much faster. So I believe refresh rates need to be increased even more if you want to get rid of all of the RowHammer errors. Okay, 2x is not bad. Maybe it covers it covers most of the errors actually. So this is employed by all of the industry because we don't have any better way of programming our memory controllers. Let me talk about some more intelligent solutions. Basically, this was our solution. It's probabilistic. It's a very simple idea basically. Whenever you close a row, you refresh or activate adjacent rows with very, very low probability. Let's say 5 times out of 1,000 times you close a row, you do this. You don't do it every time clearly. If you do it every time, it's going to be a lot of overhead. But you don't refresh the entire memory like this one. You just refresh the adjacent rows, physically adjacent rows. And we showed that this is actually very low overhead. You get very good reliability guarantees. You can get rid of all of the errors essentially. And the overhead is over here, much better than increasing the refresh rate by 2x or 4x or 7x, whatever you want to increase that. And it's also low cost and low complexity. You don't need to track which rows are being accessed a lot, because this is not based on that. This is probabilistic and low complexity. And I believe it's actually a good solution. It's actually being implemented. Variants of it are being implemented in DRAM chips and also the memory controllers that we will see. Now, if you implement in DRAM chip, the way manufacturers are doing, I think there's limited possibility. I don't like this as much, but it's good that people are trying to do it. What people are trying to do is there's enough slack and timing parameters that you have in DRAM today, because data sheets specify some value. For example, after a precharge, you need to wait, let's say 15 nanoseconds. But the precharge itself really takes 5 nanoseconds internally. So there's a huge timing slack, 10 nanoseconds, where manufacturers could use to inject a refresh to the adjacent rows. That's an example. Keep this as an example. They also inject refreshes and refresh intervals, ... And there's actually a lot of slack today, actually. I think this is possible to do under some conditions. But slack changes over time. Slack changes over temperature. So this is not a good solution to rely on in general, in my opinion. And the other thing is we want to get rid of the slack. Actually, this latency slack is one of the big problems with long latencies. If you get rid of that slack, you can reduce DRAM latencies by a lot. So I don't think this is a good solution from a fundamental perspective. I think this is a much more principled and better solution, because you divide the responsibility between DRAM and memory controller. Memory controller basically orchestrates these failure mechanisms so that it actually solves the problem. Now, the good news is, the downside is, do we need a break?
Yeah.
Okay, let me finish this part and then we'll conclude. We're almost done with a little bit. But basically, the downside of this solution is the memory controller needs to know which rows are adjacent, right? And this information, I think, is sadly not communicated to the memory controller today. I think going forward, this needs to change. Now, this didn't prevent Intel from actually implementing the solution. Intel has this memory controller. Now, this is not exactly what we envisioned, but in the BIOS, you can program the memory controller and pick your RowHammer solution, hardware RowHammer protection or 2x refresh. Now, hardware RowHammer protection basically does something very similar to a probabilistic adjacent row activation, where you can choose the RowHammer activation probability. What's the probability at which you're going to issue and activate after a precharge? Now, the good news is this and slightly more intelligent memory controller as we envisioned. The bad news is probably it's not going to cover all cases, because I do not believe that they know exactly row adjacency information in the memory controller. Now, they might do some reverse engineering, but if you really want to know this, it's a lot of reverse engineering, because we've done it in our work. So I think the real solution going forward builds on what this real memory controller started, but it does it dynamically while the system is operating. Okay, if you're interested, I think there's a lot more to say. But basically, main memory controllers needs intelligent controllers. Main memory needs intelligent controllers for security also. And as I said, industry is writing papers about it too. They're also, even though this paper is not about RowHammer at all, it's about other scaling challenges. I think you can add RowHammer as another scaling challenge over here. And the solution that's proposed is going to be similar. You have a more intelligent memory controller to tolerate the errors. Now, these intelligent memory controllers actually exist. Flash memory, for example, has these intelligent controls. Flash memory is a memory type that doesn't work without intelligent controllers because you get a lot of errors. And it's fascinating, actually. We did a lot of work. We still do a lot of work on flash memory. Actually, we started doing work on flash memory before we started doing work on DRAM. And these research tracks were synergistic with each other. We knew read disturb errors were problems in flash memory, so we started looking into read disturb errors in DRAM also. And we built this FPGA-based infrastructure in flash memory. And if you're interested in this, we've written a lot of papers, but this is a summary paper that we wrote to summarize 8 years of research plus what's happening in industry in terms of error mitigation in flash memory-based solid-state drives. But basically, my key takeaway is we need intelligent controllers to overcome the security issues, reliability issues, and scaling issues in general, which lead to the security and reliability issues. I think if I don't stop, you're going to stop me. So this is a good place, a good break point to stop. And then we'll pick up with this one, and then finish the RowHammer, and then we'll continue with computation and memory. Does that sound good? Okay, now it's time for a break.
Yeah. Thank you very much.
Thank you. Okay, I guess we can get started. So good news is we've covered a lot of RowHammer. I'm going to very briefly talk about, wrap up the RowHammer, and then we're going to jump into computation and memory. And who knows, maybe we'll be able to cover everything. Unlikely, but we'll try. Feel free to ask questions. I mean, we don't have to cover everything in the end. Okay. So RowHammer is very interesting, but I think there are going to be even more interesting things coming into the future. Basically, DRAM is becoming less reliable, more vulnerable, and I've given you examples of this. I'm not going to repeat this again. We've also been doing large-scale studies on flash memory with Facebook, for example, in this case. It's also fascinating to do these large-scale studies on other memory types as well. I'm not going to talk about that, but this is an aside. This shows that flash memory is also becoming worse in the future. So I think due to difficulties that we see in these technology scaling of memories, other problems may also appear, or some of them may be going unnoticed. We don't know exactly. Some errors may already be slipping into the field. Clearly, RowHammer slipped into the field. Retention errors, as I said, may be slipping into the field because these are very difficult to detect at this point. Read errors, write errors, and who knows what else. I think understanding which errors are slipping into the field and discovering them can be very important. As we will see, I think RowHammer had a lot of really interesting benefits after it was discovered. I believe some of these errors will have a lot of interesting benefits after they're discovered and shown that they're slipping into the field. Because they're not only reliability problems, they're also security problems, as we have discussed already. So we already talked about retention errors. Normally, if we had time, I would talk a lot more about them, but we don't have time. So I would refer you to the papers and what we've discussed so far. But I'll end up with this one. Basically, determining the data retention time of a cell or row is getting more difficult for the reasons that we've already discussed. Data pattern dependence and variable retention time. As a result, some retention errors may already be slipping into the field. So we need to guard against them somehow. I think intelligent controls are really needed for this purpose. Now let me give you some broad research directions as I think of them. How do we keep future memory secure? And hopefully this will be a bit fun also. So basically there are a lot of memories. DRAM, flash memory, these are memories we know, but there are also memories we don't know as well, like phase change memory, 3DX point, STT-MRAM, memristors, carbon nanotubes. They all have reliability issues. They all have, even though they're scalable, they still have reliability issues, and some of them have endurance issues also. When you can only do so many writes to some of these cells in these memories. So the key question is actually how do we design fundamentally secure, reliable, and safe architectures in the presence of these memories that are scaling and that are unreliable fundamentally, right? Because even DRAM is unreliable fundamentally, right? You have to refresh it. It's really a reliability problem. Technology is not reliable. So I think, let me give you the broad research direction that I have in mind. I don't have all details, but RowHammer is a good example of this one, for example. Somehow we need to design fundamentally secure computing architecture. Somehow we need to have the infrastructure to predict and prevent such safety or reliability and security issues. And I think this is a good methodology, in my opinion, to approach the problem. First of all, we need to understand based on what we have. We need to develop methods for vulnerability modeling and discovery of these issues. Can we model and predict based on real data and analysis? I think we need to really attack the problem with the real devices as well as modeling and simulation. we need to understand the vulnerabilities somehow, and we need to develop reliable metrics. You can think of this in the context of memory reliability, but you can also think of this in terms of exploits like Meltdown and Spectre. I think we really need to understand where we are vulnerable and where we're not vulnerable, and how do we actually close the vulnerability with different metrics. And on top of this, we need to architect. We need to design principled architectures with security as key concern. We've focused a lot on performance and cost over decades and decades. Recently, more energy, and maybe security will be even more into the future, right? So we need to somehow have good partitioning of duties across the stack, like memory and memory controller is important. We cannot give up performance and efficiency, that's for sure. I think any solution that gives you security, getting rid of performance and efficiency, is not a general purpose solution. Very special purpose cases maybe, but general purpose, you really need these two. And I think one thing that's really necessary is patchability in the field. We're designing these structures that are very rigid. They don't have much patchability, like memory controllers can only do additional refreshes. I think going forward we need more patchability, more programmability, more reconfigurability in the field, and that really helps patching for errors, I think, or security vulnerabilities that we find later on. Because as I mentioned, I don't think we can anticipate all of the security vulnerabilities 5 years or 10 years down the road. And I think on top of this, we want really to think about designing for security from the very basic low levels of the architecture. How do we design different blocks for security? How do we test these different blocks for security? So we will need high coverage and good interaction with other system reliability methods. In my opinion, not only patchability, but online testing, online profiling of different components in the system, so that you dynamically find out these security and reliability vulnerabilities is a good idea. Because again, you cannot cover for all cases, and systems change over time. If you actually do your online testing after you ship the product, like online testing memory controllers, that can figure out what are the different issues, that can enable much better systems. Again, this is very high level as we discussed. But that's why we've been building these infrastructures to really understand DRAM, for example. We've been building infrastructures to understand Flash also. And as I've given you a lot of reference in these, so you can take a look at them. So let's take a look at over here. We call this bridge, right? I think bridges are infrastructures. I'm going to finish the bridge analogy, if you will. Bridges are very critical infrastructure, clearly. But bridges don't possess something that computing devices possess. Computing devices actually are very patchable and reconfigurable, programmable. You can avoid these things. It's very hard to do this with this sort of infrastructure. How do you make it reconfigurable? How do you make it patchable, right? As a result, even though people have been building bridges for a really long time, things happen. These are some incidents. Actually, something very familiar to Italy will come soon. But this is the Han River in Seoul, Korea, 1994. This was actually a big incident at that time. For those of you who were alive at that time, some of you are younger, I think. But this actually is not as nice of a story as the Galloping Gertie, because a lot of people died in this case. This is another example in Minneapolis in 2007. This is Genoa in 2018. So we've been building bridges for a long time, but we don't know how to patch them. But I think in computing we have a luxury. We really can patch these devices, so we really should be patching them, meaning we really should be designing them such that they're patchable in the field or reconfigurable in the field. And I think that requires intelligence again, so that we can avoid such failures. Let me give you some final thoughts on RowHammer, and I think we'll conclude this part. I've already said this. I think this is also important, how to exploit and fix the vulnerabilities. Actually, people have come up with really a lot of innovative attacks by understanding how things work across the hardware and the software. So I think this is a very good example of hardware-software co-design and understanding what happens in hardware and how do you actually take advantage of it in the software. Of course, from an attack perspective. I've already discussed this, so I'm going to skip that. So how many people know about Byzantine failures? So these are failures. Byzantine general's problem. Leslie Lamport, who was a Turing Award winner, he introduced these failures. Basically, you have Byzantine generals, and some of them are not reliable. And how do you still build an army that can tolerate these unreliable generals or traitors, let's say, right? That's the idea. So he has this theory. I'm not going to talk about this. It's a beautiful transaction on programming language and systems paper. But these sort of RowHammer type of failures are also called Byzantine failures. Now, these Byzantine failures are characterized by undetected erroneous computation. Basically, you get an error, you don't even know that you have it. Like a traitor Byzantine general, right? You trust this general, they're going to do the right thing, but they're really causing errors. Now this is the opposite of exactly what you want in a reliable system. You either fail fast, well, you basically fail fast. You fail with an error, or you give no result in the end. Of course, doing this is important in systems going forward. So the interesting thing is, if you're in this Byzantine failure mode, what has errors can also be malicious. The only distinction between reliability and security is really intent in the end. Reliability is a failure mode, it gives you errors, and somebody can exploit those errors, especially if they can be exploited predictably. That's why these Byzantine failures have had a lot of impact. Basically, it's very difficult to detect and confine this sort of Byzantine failures. So you should really do all you can to avoid them. That's why people really should solve the RowHammer problem and protect systems against it. And if you're really interested in the Byzantine generals problem, you can take a look at this paper. It's 37 years ago by Leslie Lamport. Okay. So I think we've already said this. RowHammer, I think the interesting part about RowHammer is it's really the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. Now, people knew bit flips were a problem, actually. There are actually security venues, for example, in IEEE Security and Privacy, it's one of the top conference in 2003. There's a publication called Attacking a Virtual Machine by Inducing Memory Errors, or something like that. Now, what these folks from Princeton did was they showed that you could go to a machine, you could heat up the memory physically, and that introduced a lot of bit flips. And they said that once you get those bit flips, you can take over the Java virtual machine. Basically get out of the sandbox so that you're not operating within the confines of the virtual machine. It's a beautiful paper. It's amazing, I think. Now the downside is, of course, you need to have physical access to this machine, right? If you have physical access to the machine, you can do even worse things, perhaps. Now what RowHammer did was it enabled a way of inducing these errors remotely without physical access by just running software on the system and predictably. So it really lowered the barrier of inducing those memory errors. Now the interesting thing is also about a mindset in the systems and security communities. People knew these bit flips are programmatic, but nobody developed attacks like what happened after RowHammer, right? Now RowHammer was there. The errors were real. Nobody needed to induce them with physical access. Now everybody developed attacks after that. This is interesting thinking, right? In computer architecture, we do a lot of simulation. The hardware doesn't need to exist for me at least, so that I can do things. But there are some communities like security where you really need the hardware to be able to develop those attacks. And it's understandable because it's real, right, at that point in time. But sometimes it may be good to think about, okay, what if it's going to be there and I simulate these attacks and develop these attacks 20 years earlier. Okay, anyway, I think it's interesting. So I think what RowHammer enabled because of this real issue is it's a new mindset that has enabled a renewed interest in hardware security attack research. Real chips are vulnerable in a simple and widespread manner. You can do this really easily, and this caused real security problems. So it's really hardware reliability and security connection is now mainstream discourse. As a result, people have developed many new RowHammer attacks. As I said, I think there's more to come. RowHammer is really getting worse in more scaled technologies, but of course the barrier is getting higher because solutions are being implemented also. Clearly manufacturers or memory control designers are not going to sit idle. The key question is, can you actually exploit some of the problems of the existing solutions? So clearly there's I think this is also very important. We need to develop new RowHammer solutions. There are many of them, clearly. And I think we need to have more principled system and DRAM co-designs for this. There are also software solutions we didn't cover. I think software solutions are also interesting. I think they're not there yet at this point. They cause a lot of overhead. I believe the real solutions should be in hardware, but I think software solutions are interesting to examine because they could help other problems going into the future. And some of those software solutions could be implementable in the hardware as well, right? That's why it's good to examine all types of solutions in this. And there's more to come, I think, over here. So I think perhaps most importantly, it's really the shift in mindset. The next part of the talk is going to be especially about more mindset. Basically, mainstream security researchers are really thinking this general purpose hardware is really fallible in a widespread manner. We should not assume hardware is reliable. Its problems are exploitable. That's why hardware security research has become even more interesting. So many system security research, as a result, started examining hardware in more depth. And they understood hardware's inner workings and vulnerabilities. And two of the groups that worked heavily on RowHammer actually got interested in other stuff in hardware. And they actually went on and discovered Meltdown and Spectre. And I think there's more to come in this direction also. Perhaps some other attacks that we haven't imagined yet. Okay, so let me summarize the RowHammer part. Clearly, DRAM reliability and memory reliability in general is reducing as you scale memory to smaller technology nodes. Reliability issues open up security vulnerabilities, and these are very hard to defend against. Byzantine failures. RowHammer is a prime example, and we already said this, and I think its implications on system security research, and I think research across the hardware-software stack are tremendous and exciting. Now, the bad news is RowHammer at a fundamental level, device level, is getting worse. The good news is we have a lot more to do as researchers, right? It's good to understand where we are vulnerable, not just about RowHammer, but in general, other reliability issues that lead to security problems. The most important thing is we're now fully aware hardware is easily fallible, and we're developing both attacks and solutions. That's why I think hardware security is very exciting today. If you look at the security menus and their evolution over the decades and decades, today is really about hardware security. The most exciting attacks are really coming from the hardware vulnerabilities that people find. Meltdown, Spectre, next versions of them. And I think people will find some other thing that's outside the Meltdown and Spectre boundary that really affects hardware in a widespread way. Okay, but basically we need to develop principled models, methodologies, and solutions to solve the problem. Okay, and if you want more, the more is in the retrospective, but I will conclude with this one.